So today we're going to learn about calorimetry, which, as you can see, it's the measure of heat changes. The word calorie is a unit for heat, and calorimetry means we have heat, which is calorie, and we're metering the heat. So calorimetry is a measure of heat. So we have some new vocabulary in here. I'm just going to open these up so you can see them. There we go. We have this variable Q, which stands for heat flow. S stands for the specific heat capacity. Delta T stands for the change in temperature. And then you're told here that the specific heat capacity is the energy needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. So you've given some notes here. A bigger specific heat capacity means the substance needs more heat per 1 gram of substance to raise the substance's temperature by 1 degree Celsius. And you're given the units here. Now this delta T, delta means change, and it's always final minus initial. So delta T means T final minus T initial. Then we have a relationship between all of these variables. Heat flow is the mass of a substance times the specific heat capacity. Heat flow is Q, mass is M, specific heat capacity is the S right here, and the temperature change is delta T. So symbolically, it looks like this. Q is ms delta T. So we'll do our first problem. I'm not going to read it out loud. All right, and this kJ stands for kilojoules. Kilojoules. So I'm going to open all of this up and then talk about where everything comes from. So remember, circle all of the given information. Here's all our given information. I'm going to put a square around what I'm trying to find. Calculate the amount of heat absorbed. I'm trying to find heat absorbed. So for my data, I'm going to write everything I know. I'm given my 466 grams, so I'm going to check that off. This 8.5 degrees Celsius, I'm going to check it off. It's right here. And I identify, oh, that's my initial temperature. And I raise the heat to 74.6. I'm going to check that off. That's my final temperature. I'm also given this specific heat capacity of water, S for water. I'm going to check that off because I've written it down here. And now the heat absorbed in kilojoules. Heat absorbed is my question. So I'm writing that down right there. So I'm going to put a little check off there. And heat absorbed, I have to figure out what variable is that. Heat is Q. Remember, heat is Q right there. So that's Q. We're trying to find Q. So now I know here's my equation right here. So here's my equation. And now I just substitute in all the values. I'm trying to find Q. So I plug in all my values. My M is right here. My S is right here. Delta T is T final minus T initial. I'm noticing I'm forgetting all my superscripts here. So these should be superscripts, these two little degrees right there. And the I here should be a subscript. The F should be a subscript. S for H2O should be a subscript. Okay, getting back to the problem at hand. I plug in my T final minus T initial. I put that in my calculator. I get this number. And I'm allowed to keep 3 sig figs because I have 3 here, 3 here. When I do this subtraction here, I will end up actually with 4 sig figs because I keep the answer to the hundredths placeholder. But altogether, I get to keep 3 sig figs. So this becomes my answer. But I asked for this in kilojoules, not in joules. So to go from joules to kilojoules, I have to divide by 1,000. And here's my final answer. All right, another problem. Oops, I'm gonna go back to draw. Heat transfer. So our first problem was just getting used to using this equation and getting familiar a little bit with the variables of heat flow. Now we're going to do heat transfer. So we need to know about the law of conservation of energy. Energy is conserved. Because energy is conserved, we get this equation. You're going to be asked later on, where does this equation come from? And you have to know this equation comes from the law of conservation of energy. Energy is conserved. Heat is energy, and it is conserved. Knowing that a Q is ms delta T. So the resulting equation is Q1 is ms delta T for substance 1. Q2 is ms delta T for substance 2. So we get this equation right here. This is a very important equation. And you will be using that in class. I just made a note here. You can read that. It's in your notes already. But I'm going to keep going. Just isolate the unknown and then plug in the numerical values. That will save you lots of time and energy, and you will get the answer correct more often. When students plug in the numbers and then try to isolate the missing variable, often more miscalculations occur. And also this negative that's right here gets students very confused. By the way, I just want to point out Q1 is negative Q2. You don't have to write this down. This is the same as negative Q1 equals positive Q2. All I need to do is multiply both sides by -1 to obtain this equation right here, because this becomes positive on the right side. Students always ask, why is Q1 negative Q2? Why isn't Q2 negative Q1? It doesn't matter which side you put the negative on. It's just by math terms, the negative can go on either side. It means the same thing mathematically. All right, problem 2, heat transfer. So we're going to do a heat transfer problem now. I'm going to uncover the left side. It's a little confusing. I'm going to circle all of my information. So I've got, I've got this, I've got this, I've got, 100 mils of water and 1 gram per mil. I put those together, and that tells me there's 100 grams of water. I've got a bunch of temperatures. I'm trying to find the heat capacity for lead, and I've got the heat capacity for water. So my lead data. So here's my mass, the lead pellet. There's the mass of the lead. Oh, here's a temperature for lead. The lead is at this temperature, so that's my initial temperature right there, Ti. Okay. Oh, now I'm on my water data, so I'm going to open up the water side here. If I can figure out how to do this without opening the middle part. Okay. Water. Oh, there we go. All right, so I have 100 grams of water right here. So I'm going to check that off. The water temperature rises from 22.5. There's my initial water temperature. And it goes up to 23.17. That would be my final temperature, because that's where I end up according to the language here. Find the heat capacity of lead. Heat capacity of lead is question mark, so I've used that. And my S for water, that's the heat capacity for water, and that's this value right here. So I will check that. I have checked everything off. Now, one thing to note, I had that up here for you already. T final is always the same for both substances. So now I actually know that this T final and this T final are the same, because your substances are in the same place. They have to end up at the same temperature. My equation was the Q1 is negative Q2, and I'm just letting lead be number 1 and water be number 2. So my Q for the lead is negative Q for the water. I could have set this up backwards. When I use the equation Q is ms delta T, I get this equation right here, that ms delta T for the lead is negative ms delta T for the water. And this is just a note that T final is the same for both substances. You don't have to write that in. I'm just pointing that out. It's important. Students often forget. They say, well, I don't know the T final for this one. It's the same temperature when you have two things in the same mixed together in the same space or volume. Okay, the missing variable is the specific heat capacity for lead. So we're going to isolate S for lead. We're going to isolate this variable right here because that is what is missing. So that means we're going to divide both sides by m delta T for lead. You do not need to write down the instructions that I write here. I'm just writing them down so that you know what's happening. So I wrote the missing variable is S for lead. So we're going to isolate S by dividing both sides of the equation by m delta T for lead before substituting in the numbers. So I just showed that symbolically. You do not need to write this out. I'm just plugging in my numbers for this equation. So I plug in my water data right here because that's the ms delta T for water. And, oh, the T delta T, don't forget that's T final minus T initial for the water. And now I'm dividing by the m delta T for lead. That's this piece right here. I'm just substituting in this information over here. And when I put that all into my calculator, I get this. There's a lot of information there. It's up to you what you want to write down in all of this. I'm going to erase all of this stuff that I wrote all over the place in case you're looking at trying to figure out what everything is here. I just plugged in my values and solved. Now let's check out our units though. So these grams, oops, these grams and these grams don't cancel. What cancels here is actually I have, what can I cancel? This is in the numerator, all my degrees Celsius, and in the denominator I've got these degrees Celsius. So I can cancel out these with these. Oh, and notice on the left side in the numerator, I've got grams and grams. So I can cancel those grams with those grams. And that's all I can cancel. So I end up with these units at the end. Just checking. You always want to write your units down and check your units. I keep noticing students skipping that step. That's not good to skip this step. And then there's a note here about why you can keep 2 sig figs only. That's in your notes. I'm not going to go over that. Then our last problem. This would be an extra credit type problem when you're solving for the final temperature in a Q1 equals negative Q2 problem. It's just mathematically more complex. So actually, I probably wouldn't even put this problem on a test because it's not testing your chemistry knowledge so much. It's testing your ability to do algebra 2 or algebra 1 actually. So, okay, I'm going to go through the problem just so you can see it. We circle everything given. I'm just circling all the given quantities. Oops, those go with those units. S for lead. Oh, here we go. This is what we're looking for. I'm putting a square around what we're trying to find. So now I can fill in my lead data. You can ignore what's down here. Okay, so I've got a number here, and here's my number. I have to identify what are grams. Oh, that's mass. Okay, so I've done that. The lead is at 75 degrees Celsius. If I'm at a certain temperature, it's telling me that's where I started. That's my TI. Now, oh, that's my water data. That's water data. Oh, I've got my specific heat for lead. Let's check that off. Here we go. It's right here. Specific heat for lead. I'm trying to find the final temperature. So I've got that checked off and I've listed it here. What's my TF? Now let's see what we know about our water data. What data do we know about the water? Let's make sure we're checking everything off. Okay, I've got 60 grams of water. That goes on the water side. And grams is mass. So that's my mass. The water is at 12.2 degrees Celsius. It's at that temperature, so that's my initial temperature. Specific heat of water right here. Let's check that off. Now remember, the final temperature is the same. It's always the same. So that's what I'm missing. I've already checked it off. Have I checked off everything? Yes, I have. So I'm in good shape so far. So now my equation is Q lead is negative Q water. And symbolically, that's the MS delta T for the lead is negative MS delta T for the water. T final is always the same for both substances. You don't have to write that down. I just put that in there as a reminder. And now let's see how we solve this. We're trying to identify T final. And remember, delta T is the TF minus TI. So for both sides, we'll have TF minus TI. I'm going to divide both sides by MS of the lead so that I get the TF minus TI of the lead by itself first. A lot of students don't like to solve it this way, and then they complicate the problem. I'm telling you, if you're solving for T final, it's always good to isolate the delta T by dividing both sides of the equation by MS of the lead, or whatever chemical you're transferring heat from or to. That gives us this equation right here. Then I plug in all of my values. So right here, I've started plugging in my values. Remember, delta T, this delta T is TF minus TI. And I did the same thing over here. Delta T is TF minus TI. It's always final minus initial. So I plug my values in and I get this kind of ugly equation right here. What's not so ugly about this equation is that I can cancel my units really nicely. They show up really well right there. And then the grams can cancel with the grams. Okay. Just realized in one of those earlier problems, I could have canceled the grams with the grams. Doesn't matter. Okay. Okay. So now I'm going to calculate this. I have to do 60 times 4.18 and then dividing that by 58.127. That will give me, there's that negative sign right there. I don't distribute this negative yet. That gives me negative 34.05. All of this stuff is 34.05. So now I'm going to distribute. I'm not doing anything with the left side yet. I just calculated what all of this was, and that's my 34.05. So I'm going to highlight all of this is where the 34.05 came from. Now I'm going to distribute that negative 34.05 into the parentheses here. So I get negative 34.05 TF. This right here becomes a positive. This becomes positive because I have a negative and a negative in front. When I distribute this negative 34.05, I get positive, and I have to multiply the 34.05 times the 12.2. So I get the 415.4. I have to keep my units, degrees Celsius. I'm going to erase all of this stuff now because you can't see what's happening below. I need to combine the like terms. So everything that has a TF, I need to combine. Here was my original left side of the equation. So I need to combine these two together. So I will add the 34.05 TF to both sides, which gives me this on the left side. And then I also need to combine the non-TF terms, my degrees Celsius pieces. So I'm going to add, because there's a negative here, I'm going to add 75 degrees Celsius to both sides. So it leaves this side and comes over here. So my right side becomes this quantity of degrees Celsius. The left side becomes this quantity of TF. When I add these together, this is just right here, that's just 1 TF. So 1 TF plus 34.05 TFs gives me 35.05 TFs. When I add this, I get 490.4 degrees Celsius. With this equation, I need to divide both sides by the 35.05. That's shown here. When I calculate that, I get 13.99 degrees Celsius. Now let's check our sig figs. I'm going to erase everything. So I notice I'm doing a lot of multiplication and division. In this piece, I could only keep 3 sig figs because there's 3 sig figs in all of those. So over here, I kept 4 only because I don't want to round too early. So I'm going to keep at least 4, and then I'll deal with the rounding later. But really, I should have kept only 3 sig figs here. Now this subtraction piece right here, I can't really work with that yet because I need to do some addition subtraction on each side. So the key to this piece right here is I'm adding and I keep to the tenths. I'm going to keep this to the tenths placeholder. So for this piece, I could actually keep 4 sig figs. This is 4 sig figs. Because I was keeping to the tenths placeholder, let me make sure. How did I get this 415? Actually, maybe I could only keep 2 sig figs because that 14 came from multiplying this with 3 sig figs, and I multiplied this into this. Actually, I could only keep 3 sig figs here, even though I kept the extra sig fig. So this one is going to actually end up at, it's really 415 degrees Celsius. Now I don't round until the end, but in terms of sig figs, this was 3 sig figs. So when I multiply that by my 12.2 sig figs, 12.2 degrees Celsius, I could only keep 3 sig figs in this number. So I have to remember, oh, this would have been only 3 sig figs. So now, in this addition piece, this is really only 3 sig figs, which means I only have that to the ones placeholder. So now I can only keep this to the ones placeholder. Wow, we lose another sig fig there. So the truly correct answer with sig figs, again, I'm not going to be taking off for sig figs in these problems, but unless you're off by more than 2 sig figs. So if you kept 4 sig figs, you'd be okay here, even though you were only supposed to keep 2. On the other side, this would have been 3 sig figs. We would have kept that to the tenths placeholder. So this left side I could have kept to 3 sig figs because I would have kept it to the tenths placeholder. And that 1 in front of the TF, that's like, we're not going to worry about those sig figs. And that's it. Okay.